You know, in the world of technology, every so often a single idea comes along, maybe in just one research paper, that changes, well, pretty much everything. Today, we're going to tear down one of those papers, a 2017 publication that didn't just tweak AI, it basically gave it a whole new brain.
And it all kicked off with this title. Just 5 words. Attention is all you need. I mean, it's so simple, it's bold, and it's basically a direct challenge to the entire way people were thinking about AI language processing back then. It was saying, hey, all that super complex machinery everyone's using, you might not need it at all. Okay, so let's get into what that really means.
To really get why this paper was such a lightning strike, we first have to talk about the problem it was trying to solve. The big roadblock for AI, the thing that was holding it back from truly understanding language, was what we can call the sequential problem.
So before this paper dropped, the undisputed champs of language AI were these things called recurrent neural networks, or RNNs. You might have heard of models like LSTMs. They were the top dogs. And their whole design was built on a simple idea: process language the way we do, or at least the way we thought we do, which is one word at a time in a nice, neat order.
But that's also its Achilles heel. I mean, imagine trying to read a long book by reading one single word, closing the book, thinking about it, then opening it back up for the next word. It's just incredibly slow. This one-at-a-time approach meant you couldn't use modern computers to process all the words in parallel, which made training these models an absolute slog. And even worse, by the time the model got to the end of a long sentence, it had often totally forgotten what was said at the beginning.
So the researchers on this paper came up with a really radical solution. They asked, what if, instead of reading word by word, a model could look at the entire sentence all at once? What if it could figure out how important every word is to every other word all at the same time? Well, this idea was called attention.
So what is an attention mechanism, really? Well, at its core, it's just a way for the model to decide what to focus on. So for example, if it's translating a sentence, it can look at all the words in the original sentence to figure out the best translation for the one word it's working on right now. It lets the model connect, say, a pronoun back to the person it's talking about, even if they're words or even sentences apart.
And you can think of it in a pretty simple way. For any given word, let's call that the query, it kind of asks a question, like, hey, who's the most important person to me in this sentence? It then looks at all the other words, and those act as keys, like little signposts for context. Based on how well a key matches the query, the model then pulls in the actual meaning or the value of those words. And what you get at the end is a brand new version of that original word, now totally supercharged with all the most important context from the entire sentence.
So here's the really brilliant part. The researchers didn't just bolt this new attention idea onto an old model. Nope. They threw out the old rulebook completely and built a brand new architecture from scratch, built only on this one concept. And they called it the transformer.
Okay, so what's under the hood of this thing? Well, the transformer has a few key parts. It uses a pretty standard encoder-decoder setup, which is great for tasks like translation. But, and this is the big but, it rips out the old recurrent layers and replaces them with something totally new: multi-head self-attention. Add in some other networks and a really clever trick for knowing word order called positional encodings, and you've got the whole package.
And this multi-head attention thing is where it gets really clever. I mean, why have just one attention mechanism when you can have, say, 8 of them running at the same time? It lets the model look at a sentence from 8 different angles or perspectives all at once. So one head might be tracking who's doing what, while another is figuring out grammar, and another is looking for something else entirely. It just creates this incredibly rich, layered understanding of the text.
But wait a minute. If you're not processing words one by one, how on earth do you know the difference between the dog bit the man and the man bit the dog? That's a huge problem, right? Well, that's where positional encodings come in. It's this super clever trick where the model adds a unique mathematical signal, kind of like a fingerprint made of sine and cosine waves, to each word based on its exact position in the sentence. This gives the model that crucial sense of order without ever having to go one by one.
Okay, so the theory was beautiful, it was elegant, but did it actually work? This is the moment of truth. This is where our research paper goes from just being a cool idea to becoming a landmark piece of history. The results.
And wow, did the results speak for themselves. This table shows how the transformer stacked up against the world's best translation models at the time. The score here is called blue. All you need to know is that higher is better. And look at that. On the tough English to German test, the big transformer didn't just beat the record, it smashed it. And on English to French, it was right up there with the best of them, even these huge, complex systems.
This number right here,
28.4. That was a new state of the art. It blew past every model that came before it, even these giant ensembles, which are basically multiple models all working together. A single transformer was better than a whole team of the old models. This was a massive, massive jump in quality.
And here's the real kicker. It wasn't just better, it was unbelievably faster to train. The paper mentions their big model set that new record after training for just 3.5 days on 8 GPUs. I mean, that is a tiny fraction of the cost and time for the models it just beat. So, it's better, it's faster, and it's cheaper to run. That's the kind of trifecta you almost never see.
So what was the secret sauce? Why was this brand new architecture so much more powerful? Well, it really boils down to two huge fundamental advantages that self-attention has over those old one-word-at-a-time methods.
This little table from the paper basically tells the entire story. Just look at that bottom row for self-attention. The number of sequential operations is O of 1, which is just a fancy way of saying it's constant. It doesn't get bigger as the sentence gets longer. And the maximum path length, how hard it is to connect any two words, is also constant. Meanwhile, look at the recurrent network at the top. Everything gets slower and harder the longer your sentence is.
And right there, that is the winning formula. Constant sequential operations means you can just throw all your computing power at the problem and process everything at once, in parallel. That makes training lightning fast. And a constant path length means the model can easily draw a direct line between the first word of a huge document and the very last word, finally solving that long-range memory problem that just crippled the older models.
So why are we still talking about this one paper today? Because that combination of efficiency and power completely unlocked the ability to scale up. The transformer architecture, that's the T in GPT, it's the engine behind pretty much every single large language model that has taken the world by storm. This paper didn't just build a slightly better translation model, it literally laid the foundation for the entire modern AI revolution.
And that leaves us with one final, really fascinating question to think about. The authors themselves ended the paper by saying they wanted to apply this to images, audio, and video. And now, we're seeing that happen. So if a simple, powerful idea like attention is all you need could completely change how we process language, what happens when that same incredible focus gets applied everywhere else?